Hello students, welcome to Vastiversity. Today we're going to be starting Calculus 1. So our first lesson is going to be review for calculus. We're going to review some of the algebra, some of the trigonometry things for us to keep in mind before we're entering the calculus. So let's go ahead and start with a function and a function definition. So a function f is a rule that assigns to each element x in a set e exactly one element called f of x in a set e. And for this course, we're going to be using the James Stewart Calculus, so single variable calculus, early transcendental, 8th edition, right? I would highly recommend. It will be used for both Calculus 1 and Calculus 2. It has great material, great questions, great problems to solve in practice, and majority of universities and colleges do rely on that specific book. All right, so let's come back to the functions. So how can we imagine the functions? So the functions can be imagined as input and output. Right? From algebra, we'll remember what a function is. So an input and the output, right? And D and E are essentially represents, D represents the domain, E represents the range. So this is the domain, this is the range. Or we can also call it input and the output. Okay, and then if we want to visualize on the graph's going to be look like this. So on the left-hand side, we have a properly defined function. Right, x-axis, y-axis. Y-axis we call the range of a function. X-axis we call the domain of the function. Okay, what does that mean for us to have a properly defined function? So in order for us to properly define a function, we got to perform a vertical line test. So a vertical line test, a curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve more than once. Alrighty, so that means if we take a look at this graphs right here, we can clearly see that the first graph, A, it's a curve, right? It's a perfect curve. It's perfectly defined a function, right? B is not, it's a curve that is not a function because a vertical line intersects two values, right, at two different points. So that violates the definition of the function. So let's also review from algebra. We learned about the absolute value function. Okay, so absolute value function is written down here. So we're going to call it absolute value. And essentially, the graph of that function looks like a V, right? And in calculus, we're going to be studying some properties regarding those kind of graphs, right, with that shape. So in algebra, you probably heard about words continuity and symmetry and maybe you heard something about differentiability. Maybe not. Right? So let's take a look at one more thing called symmetry. So for symmetry, right, we did it from algebra. For symmetry purposes, if function f, so function f is called even if f of negative x is equal to f of x. So essentially f of x absorbs the negative sign, right? So for example, a square function, right? An example would be something like, so f of negative x is equal to negative x squared, which is equal to x squared. And then the function called odd. So if it follows this property, negative x is equal to negative f of x, so we can factor out the negative sign. An example for it would be f of negative x is equal to negative x cubed. It's going to be negative x cubed. Okay, so essentially took out the negative sign and it became negative. So if we want to draw an even function, right, this is going to be even function, right? You see how it's symmetric, the even function. And then on the right hand side, we will see the odd function. So this is the odd function. All right. So, and of course, you know, function is able to increase and decrease, as we can see, right? If we're moving from, negative x to 0, we are decreasing, and then past 0, we start to increase. Same thing here, we increase, and then we start to decrease and decrease and decrease, right? So functions can be increasing and decreasing. So let's give a definition here. proper definition of what it means for a function to increase and decrease. So a function f is called increasing if on an interval I, or on interval I, if f of x1 is less than, so strictly less than f of x2, right, is called, so monotonically increasing, right? This is the important part. It's monotonically increasing in the interval. So as x grows, essentially, the function grows. And the function is called monotonically decreasing on interval I if f of x1 is greater than f of x2, whenever x1 is less than x2 on the interval I. Okay, and then, all right, so this is going to be increasing, decreasing functions, and you can review some of the problems in my algebra playlist that are going to have a link to attached in the description. So we also learned in algebra, we learned linear models, right? So linear models are based on linear equations. So the linear model is y equals to mx plus b, right? So in this case, m we call a slope, and that is rise over run. Meanwhile, b, it's an intersection, specifically 0 comma b. And so when x is equal to 0, we're going to be intersecting the y-axis. Okay, then we also had a quadratic equation. So a quadratic model. A quadratic model, so y is equal to a squared plus b and c, so plus bx plus c. Right, this is a quadratic equation. So some of the examples of the quadratic equations can be viewed in the following graph. Right, so here we are. We can have quadratic equations, so parabola looking upwards, parabola looking downwards. And of course, we can have a higher order polynomials. Right, so polynomials can be orders. So here are going to be a few of the higher order polynomials, right? And you can take a look at them and see how they're drawn. And of course, the basic polynomials, which are, x first power, x to the second power, x to the third power, etc., are going to be looking like this. Right, we usually don't see anything above x to the fourth power or x to the fifth power, but sometimes it might appear, right? So the difference between, let's say, x to the second, x to the fourth, x to the sixth, right here is going to be a good depicted of what's the difference between x to the 2, x to the 4, x to the 6, right? So we become more and more steeper. And here, same thing for the odd powers. For odd powers, we also become steeper, but on both ends. Alrighty. So we also learned the rational function, right? Rational functions and rational models. So rational functions, so f of x is a rational function if we have p of x over q of x. Okay, and q of x is not equal to 0. And okay, so let's take a look at some of the rational functions and their corresponding graphs. So for rational functions, here we have some of the graphs. We can have 1 over x. We can have, this is 1 over x more depicting. And then here is 2x to the 4 minus x squared plus 1, and x squared minus 4. So definitely review the synthetic division and all of the algorithms for the partial fraction decomposition. Right, it will be important, not for Calc 1, but still keep it refreshed for yourself, because Calc 2 will be heavy on the fractional and rational functions in general. Now, let's go ahead and talk about some of the trigonometric functions. Right, two classic trigonometric functions that we care the most about are sine and cosine. So, let's try to write it out here. So, trigonometric functions. Okay, so the graph of sine and cosine is going to be as following. So here is sine, here is cosine. So you see sine is slightly shifted, cosine is perfectly in the middle. So sine is an odd function. Sine of negative x is equal to negative sine of x. Cosine is an even function. Cosine of negative x is equal to cosine of x. Okay, so sine and cosine are defined as following. So you can notice from the graph, but I'm just going to put it out here as well. So sine is between -1 and 1 included, and cosine is between -1 and 1 included. So here we have to also remember that the unit circle, so definitely review for the unit circle, remember the values, at least the first quadrant of the first circle, of the unit circle. So here are also some properties of sine and cosine that we can add here. So sine of x plus 2 pi is equal to sine x. Cosine of x plus 2 pi is cosine of x, because those are periodic functions. So tangent, right? Tangent of x is equal to sine x over cosine x. Then cotangent of x is going to be cosine of x over sine of x. Then secant of x is going to be 1 over cosine of x. And cosecant of x is going to be 1 over sine of x. Okay? And one of the most important drawings here is going to be the tangent drawing. So let's go ahead and draw the tangent. So here is going to be tangent of x. All right. Perfect. So one more thing we learned in algebra were exponential functions. So let's go ahead and, well, before we move on to exponential functions, let's briefly mention them. So exponential functions, we have, exponential functions and logarithmic functions, so which have a different basis, right? So exponents like this, and then logarithm was looking like this. We're going to dive deep into it in a bit. First, let's review what we can do in general with a function, right? So here is the logarithms and how they look like. So there's different kind of logarithms, there's different kind of exponential functions. All right, so now let's go ahead and take a look at, essentially, before we move on to exponential and logarithmic functions, let's remember how we can even modify functions. So in order for us to modify a function, we can have vertical and horizontal shift. So suppose c is greater than 0. To obtain the graph of, y is equal to f of x plus c, shift the graph of y at distance c units upwards, minus c, shift it distance c units downwards. If it's c is in parentheses, then shift distance c units to the right, and then plus c is going to be shift distance to the left. Right, and to be more graphically, to easier visualize, let's go ahead and add this here. So we can have all kinds of interpretation here, right? So here's our f of x. We can move it upward, we can move it downward, we can move it to the right, we can move it to the left. Right, similarly, if we multiply by c, divide by c, multiply by a negative number, or add a negative, we can reflect it among the y-axis, right? So that's called vertical and horizontal stretching and reflecting, right? So the second part, which are the second graph for it, is going to be here. So we can do vertical stretching. So suppose c is greater than 1. So if we want to obtain c of f of x, which is right here, stretch the graph of y vertically by a factor of c. 1 over c, shrink the graph vertically by a factor of c. Shrink the graph of y horizontally by a factor of c. Stretch the graph horizontally by a factor of c. Negative is going to be reflect above the x-axis. Negative x inside, reflect the graph above the y-axis. Okay, so an example that will be commonly used in trigonometric functions. Right, trigonometric functions and periodic functions are very important, especially for calculus. So here would be some of the graph depicting shifts of cosines here and here, right, for different periods specifically. And then here we can also take a look at shifting the power functions, so specifically the root functions, so square root of functions. So here we can just a regular function, then 2 units down, then 2 units to the right, then flip it, then stretch 2 units upwards, and then flip it to the negative direction. Okay, so now let's go ahead and remember the composition functions, because we can combine all of those functions as a composition. So let's remember the composition that we learned in algebra. So given the two functions, f and g, the composite of function f and g, also called the composition of f and g, is defined by the following. So f composition of g of x is equal to f of g of x. Right, and here is going to be essentially an example. right? So we have an input into G, and we're processing G of X, then input into F, and it becomes F of G of X. So the F of G machine is composed of the G machine first, and then F machine on top of G machine, essentially. Right, so first we evaluate the G of X, and then we're going to be, based on the value we received from G of X, we're going to get the value of F of X. Okay, so now, since we know already how to compose functions, how to do shifts of functions, let's actually enter the exponential. So exponential functions are defined as f of x is equal to b to the power of x, where b is the base, right? And x is the power. X is the power. So we have a base, we have a power. So we can have special bases, we can have special powers, which we learned in algebra. But some of the common graphs of the exponential function is going to be like this. So we can have 1/2, 1/4, 10 to the x, 4 to the x, 2 to the x, 1/2 to the x, 1 to the x. So 1 to the x doesn't really change. And so, okay, that's just the common graphs. And what are the common laws of exponential? What are the common laws? They are going to be as following, right? So if a and b are positive numbers, and x and y are any real numbers, then b to the power of x plus y is the same thing as b to the power of x times b to the power of y. Then b to the power of x minus y is going to be b to the power of x divided by b to the power of y. B to the power of x to the power of y is going to be b to the power of x times y. B to the power of ab to the power of x is a to the power of x, and b to the power of x. So one of the special exponents. So special exponents is the Euler's number, which is e, and it's equal to 2.718 ... Right, it's an e number. So the e, or we call it a natural exponent, or it's used in natural logarithm, which we're going to be our next topic. But the graph of it is, not much different compared to any other exponent. It just has this base. And in this class, in Calculus 1, we will actually be able to find that number and properly define it and actually see where Euler got that number from. All right. Now let's talk about the inverse functions. So the inverse functions are going to be as following. So essentially, we're trying to get from y back to x, right? And here is going to be an example, right? So sometimes we have a function that takes that is a one-on-one function. So that function is important, right? Because so one x value is equal to one y value. So one x value cannot be equal to two y values, right? So for example, f is 1-to-1, we can have an inverse. G is not 1-to-1, so we cannot have an inverse. Okay? So this is an important concept from when we learned algebra about the exponentials. So exponentials, and specifically about the inverse. Okay, so the definition of inverse. A function f is called one-to-one function if it never takes on the same value twice, right? So this is important. So it doesn't take the same value twice. And how do we check that, right? How do we even know sometimes that the function, it does not do that? So we can use a horizontal line test. So a horizontal line test. So a function is 1-to-1 if and only if no horizontal line intersects its graph more than once. Okay, so what would be an example? Right, what would be an example? So a cubic function would be a 1-to-1, but a quadratic function would not. Right, so for quadratic function, here's would be an example. Right, we have to be very careful. Right, for a cubic function, so what's the inverse of the cubic? So we write inverse as f to the -1 of x. It's going to be cube root of x. Right, x can be anything from -infinity to +infinity. Doesn't matter. Meanwhile, for this one, even though x here in domain is -infinity to +infinity, our inverse will only be square root of x, and we can only be here from 0. So from x to be 0 to +infinity, because we cannot have a negative square roots, because for negative square roots, we will go into complex numbers. Okay, so let's go ahead and give a proper definition of the inverse function. So the definition of the inverse function: let f be one-on-one function with domain A and the range B. Then its inverse function f to the -1 has domain B and range A, and it's defined by So the inverse is x, so it's going to be f of x is equal to y for any y in B. Okay, so we can visualize it as following. Or we can do it two ways. We can essentially domain of f of negative. F inverse is going to be f. The range of f. So range of f of the inverse is going to be now the domain of f. Right, and well, if we have two lines, right, essentially, x and y, right, then f takes from x to y, inverse takes from y to x, right? That's essentially what it does. So, okay. And then one of the identity properties of the inverse functions. So this is something that all of the inverse functions should be able to do, since they're one-to-one, is the following. The inverse of f of x is just x. Function of inverse is just going to x. So function and inverse cancel out in both ways. So how do we find the inverse function, though? Right? So remember, how to find the inverse function? You have to follow the following process. Right? So step one, write y equal to f of x. Solve this equation in terms of y if possible. So essentially what you're trying to do, well, you're trying to flip it now. You're going to say that x is equal to f of y, and you're trying to solve for y again. And that the new y will be your inverse. And then express f of inverse of f as a function of x, interchange x and y, and result in the equation. Okay, so that's how we would be able to find the inverse of the function. Okay, so, all right. Then now, so one of the inverse functions, and the most common inverse function over the exponentials, are going to be logarithms, right? Logarithms are inverse of the exponential. Okay, so again, we had a drawing, right? We had a drawing of the logarithm. So here is an exponential function, b to the x, and here is the inverse, which is a logarithm function. So in order for us to actually find the inverse, right, what we have to do, we have to reflect the graph of the inverse by reflecting the graph of f about the line y equal to x. Okay, so now for logarithms, what are the main rules for logarithms? Is essentially the rule that it's an inverse of the exponential, right? So the first rule is going to be this. So logarithm base b of x, right, b is the base, is equal to y, which means that b to the power of y is equal to x. And then here, some of the restrictions on the logarithm. So the restrictions are as following. Logarithm base b of x is equal to x for every x belonging to the real numbers, and b to the power of logarithm of bx is equal to x for every x greater than 0. And so the most important part is, of course, the laws of logarithm. So the algebraic rules for logarithm. The law of logarithms: if x and y are positive numbers, then logarithm base b of x y is going to be logarithm base b of x logarithm base plus logarithm base of y. Okay, then logarithm base b of x over y, we're going to have logarithm base b of x minus logarithm base b of y. Logarithm base b of x to the power of r is equal to r times logarithm of base b of x. Okay, then remember the Euler's number. So for Euler's number, we're going to have a special logarithm, right? And we call it natural logarithm. Okay, so natural logarithm is a very important part for calculus, and it has few rules, of course, right? So the same thing as we had for the just exponentials and logarithms, but here is going to be specifically for the Euler's number. And of course, the natural logarithm of e is going to be equal to 1, right? Because it's the same thing as logarithm base e of e, which is 1. All right, so of course, if we would decide to change the base, because sometimes in order for us to solve a problem or to simplify it, we need to be able to change the base of the logarithm. So here, changing of base. So for any positive number b, where b is not equal to 1, we have that logarithm base b of x is equal to ln of x over ln of b, right? And we chose the natural logarithm specifically for that reason. Okay, now let's talk about more inverses. So now how about the inverse of the trigonometric functions? Right, so we can have arcsine, arccosine, arctangent, arccotangent, arcsecant, arccosecant. But we can also write it like this, right? So this is arc sine of x. So based on the books you're reading or the mathematical research journals, you might see different notations, but they all mean the same thing, right? One of the very key things for students to not miss is the following. So sine to the -1 of x is not equal to 1 over sine x. This is inverse, right? Not a fraction. This is an inverse, not a fraction. So keep that in mind. Okay, but sine has the same properties as all of the inverse functions, right? So we can have sine of inverse of sine of x is equal to x in the domain of it, and sine of sine of negative x equal to x in the domain or the range of x here, both ranges of x. So for cosine, we're going to have something very similar. The cosine is going to be as following. So the cosine of x is going to, the inverse cosine of x is equal to y, so cosine of y is equal to x, goes between 0 to y, and it has similar properties to what the sine did. So cosine, so inverse cosine of cosine x, so x is going to be between 0 and pi. Cosine of cosine inverse of x is equal to x for -1 to 1. Then tangent is going to be resembling the sine properties, right? So here are the inverse of the tangent. And of course, we also are able to have the inverses of the secant, cosecant, and cotangent, right? That are not often used in calculus, but they do exist. Okay, so that was all covered in essentially algebra and trigonometry course. So one few more things to add on this is, of course, the trigonometric identities. All right, so some of the most important trigonometric identities are, of course, the following. Sine square x plus cosine square x is equal to 1. Then we also have 1 plus tangent square x is equal to secant square x. Then 1 plus cotangent square x is equal to cosecant square x. Okay, then we have sine of pi over 2 minus x is cosine of x. Then cosine of pi over 2 minus x is equal to sine of x. Okay, and then tangent of pi over 2 minus x is equal to cotangent of x, and cotangent of pi over 2 minus x is equal to tangent. So that was more of a crash course review, right? We didn't get to solve many problems because obviously it's a very dense review session for the serial wise, so I would highly recommend you to watch the playlists on certain topics. If you feel that you're not sure about trigonometric identity, some of the algebraic operations like synthetic division or division algorithms, or any exponential so logarithmic, please check out the link in the description. And guys, and see you all next lesson.